forgot the question. Does the P line make it, the S, or does the
No.
F gene make it?
The F gene makes this place.
Okay, so
Codes
can
for
you
the
have the
pipes.
F gene without having that little P line or whatever?
No.
Okay, so the F gene, you're
But
always
you can
gonna
have a
F
plasmid that doesn't have an F gene.
Okay.
There are 36 different kinds of plasmids. Only
Okay.
one of them is an F plasmid.
Only, okay, so it's F.
And then once it transfers it, the other one grows little pili too, right?
Right, because the first gene that's transferred is the F gene. So first it finds a girlfriend that doesn't have an F plasmid, and then it doubles itself. Then it makes a little tube, and the first gene that's passed is the F gene. And if allowed to long enough, it can transfer the whole plasmid.
Can a donor cell have more than one F?
Yes. Okay, so, and you know, they can also conjugate with more than one at once. All right. We've also found that plasmids, if you bring this, remember most of the time, is between two gram-negatives that are closely related in the same genus. But remember, there's Streptococcus, it's a ho-ho. Actually, it's a slut. It doesn't get paid for it. It will have sex with anything. It doesn't matter if it's eukaryotic, prokaryotic, it's in the same genus or not. And then we have the races, Homophilus and Neisseria, that will only have sex with the same genus and the same species as they already are. So that's not getting recombination. They're already having sex with somebody that looks just like them. So anyway, this one does move a lot of DNA, but in nature, it's very restrictive because it's usually between the same genus except for Streptococcus. Okay, so it can, however, move 51. I'm not going to go over that, not going to go over that, not going to go over that. A lot of people thought, well, what are the different kinds of plasmids? You only have to know the F plasmid, but these are some of the plasmids they have discovered.
So, but we don't need to know none of this, right?
Just the F plasmid.
Just the F
You
plasmid.
just need to know that not all plasmids are F plasmids. All right. What else? Conjugation, the significance of conjugation. It's huge because if we had to discover conjugation, we wouldn't discover plasmids. If we didn't discover plasmids, there would have been no recombinant. Remember, when we took that human gene and knocked out the introns, we put it on a plasmid. Then we cloned the plasmid and had it jump into the E. coli because plasmids rule. So without conjugation, we would have never done recombinant DNA technology. We wouldn't have human insulin or human growth hormone. Okay, and so remember the conclusion. It has had a large effect on evolution of the gram-negatives because it can move up to 51 genes, but nothing else. Okay, so that leads us to our little video. And maybe it'll work and maybe it won't. We'll see. Did you hit the VCR button? We'll see if this thing will play or not. I am unsure. If it doesn't, I'll just talk about it for a few minutes. Everybody got a copy of the sheet, worksheet? Anybody need one? One of them you can already answer. Why don't we call it genetic engineering anymore? Yeah, that's it. Oh, okay. Oh, okay. All right, so you can already answer number 4. You can also answer number 2 already. What was the first organism to put human genes in?
A sheep.
The first organism on Earth that received a human gene. E. coli, human insulin. Number 4, I already told you what transgenic is. Yep, eukaryotic to eukaryotic. See if I can find. Yeah.
For midterm,
because it's on the cards, it's called a left right.
Oh,
I have a feeling I may have to go
Procombinant?
what?
Is eukaryotic prokaryotic?
I'll try this one.
DNA transfer, right?
Unlikely that it will work. Oh, this one should work.
Control number 17 is so about the lottery. Right?
should we have no?
So read through the questions real quickly so you're familiar with them. You can answer 11,
Oh, quick question on the,
9,
Lucille P. Markey Charitable Trust, the George
I'll
P.
give it
Smith
to you.
Fund, the Corporation for Public Broadcasting, viewers like you, and the people of the Upjohn Company.
you already know number
Advancing
17, I already told you.
Enhancing life. Upjohn.
A new life begins. An embryo grows and divides. What it will become, mouse or elephant, pig or person, has already been decided by the genes it inherited. Only mice pass on mouse genes. Only people pass on human genes. Until today. Because today, science has broken the barrier that separates species. Today, elephant genes can be put into mice, fish genes into tomatoes, human genes into pigs. We have begun to design life to order. Some of these designer animals are already grazing the hills of Scotland. They are owned not by a farmer, but by a new kind of company, a biotechnology company. And they are being raised not for their wool and meat, but for a life-saving drug they produce in their milk. To some, they are an exciting portent of the future.
So what do I see when I see a flock of sheep? Well, I see profits, of course, in the future. Some return for the investors that back the work that we've done so far. I also see a living embodiment of a piece of very clever science, something that started off as an idea. It's now there and it's working.
To others, the science that has created these sheep to make drugs instead of wool is taking the exploitation of animals too far.
They got two weird
raises
people. They got
profound,
somebody that's against everything
medical,
and somebody that's for
ethical
everything.
questions. It's altering
He's against
the
everything.
created order, and I think there's something profoundly subtle that we don't fully understand about the created order, and we shouldn't mess with Mother Nature to that degree.
The sheep on this research farm look and act just like any other sheep, but they are worth tens of thousands of dollars each. What makes them so different, so valuable to their owners, so disturbing to some critics, is that tucked away within the 100,000 genes that make each of them a sheep is one gene that comes from a human.
Throughout history, we've been fascinated and haunted by the idea of creatures that are part human, or humans that are part creature. Chimeras, they're called, fantastical imaginings.
From the centaur, part horse, part man, of Greek mythology, to the monster myths of the 20th century, the idea of merging animals with humans is profoundly unsettling. Whether it's Dracula, the original Batman, or a werewolf, Wolfman. Today's chimera fantasies exploit the trappings of genetic research to explain how Jeff Goldblum, in the 1986 version of The Fly, became blended with a housefly.
Sense? No, up here. Got pretty good at it, haven't I?
The Fly is science fiction, but genetic chimeras are science fact, thanks to the biological revolution that began with the discovery of the double helix of DNA. DNA is the material our genes are made of, and the genetic instructions themselves are written out using a code of just 4 letters, the initials of the chemicals that make the rungs of the double helix. It takes 6 billion C's and G's, A's and T's, to encode the instructions to make and operate a human body. Write out those letters on paper and pack them away in drawers, and you get a sense of the enormous amount of information we possess in our genes. Until very recently, this archive has been invisible, unreadable. But today, we can open the drawers of our genetic archive and read its pages. Read in the strings of hundreds or even thousands of letters that make up each gene, the instructions for making a human being.
And now we can do what has always seemed impossible. We can take from our genetic archive the genes that make us human and put them into other living creatures. An entire industry is being created to exploit this technology. One of the most remarkable aspects of this new power over our genes is how simple the tools are. They're so simple, even a child can use them.
Don't believe these people.
Okay, so that's what we can do now.
Look at their
Science found this technique,
Watch 'em.
and we can take any cells we want, and we can put in any
These
gene
kids
that we
don't
want.
know crap.
What organism?
Margaret Henderson is teaching 8th grade genetic engineering.
Information, we put DNA in, and we're actually changing the cell with DNA. Does anybody know of an organism that actually...
These students will do something unthinkable even a generation ago. Move a gene from one species into another. The organism they will engineer is a common bacterium that normally lives in our gut, but will also grow in a laboratory dish. The bacterial cells are scraped up with a wire. They are put into a test tube.
Okay. Now, make sure you get that all the way down to the bottom.
Now, DNA is added. DNA that could come from any creature on the planet.
Finish the other one? That's it. I mean, just finish this.
The bacteria and the foreign DNA are cooled, heated, and cooled again. And that's that. In 24 hours, a few of the bacterial cells will have taken up the foreign DNA and begun to treat it as their own. And that means they will carry out the foreign DNA's orders, making what the foreign DNA instructs them to make. Written in the coded rungs of the double helix, the DNA's instructions are first copied out into a messenger molecule. As the helix recoils, the message is translated by tiny cellular machines into a protein. So if the DNA put into the bacteria is human, that means the bacteria will start making human proteins. And it so happens that many human proteins can be enormously valuable drugs. It was this promise that on October 14, 1981, triggered a record day on Wall Street. That day, the first company founded to exploit the new gene technology went public. In an hour, the asking price had tripled. The biotechnology boom had arrived. In the next decade, billions of dollars poured into hundreds of new companies.
And only 4 survived
The
in the
lure?
United States.
That human proteins made in non-human cells would become wonder drugs against deadly diseases like heart attacks, stroke, diabetes, cancer. But despite the huge capital investment, the biotechnology industry has been slow to deliver on its promise.
Millions of dollars.
One problem, scaling up from lab to factory. Growing the cells that contained new human genes and harvesting the human product needed hugely complex plants of tubing and vats, all to do what living animals do naturally.
We began to realize just how inefficient the process was. And we began to wonder, is there a better way of doing this?
Instead of building a protein factory from steel and plastic and glass, why not simply co-opt one nature has already built? Alan Smith of the company Genzyme was one of the first to wonder if by putting human genes into whole animals, the animals could be employed as living factories for human proteins.
If we ask the question, where is protein made in a living animal, we could say it's made in the blood, it's certainly made in the milk, and there's a certain amount of protein in urine, and we certainly considered urine as a certain source of proteins. But milk is by far the most attractive in the sense that it's accessible.
Milk isn't only accessible, it's made in great quantities in the cells of the mammary gland. The main protein in milk is called casein. Casein is made by a gene that's only switched on in the mammary gland. The genetic on switch is next door to the casein gene. Smith used the tools of genetic engineering to sniff out the mouse casein gene and replace it with a human gene. Now, his problem was to get his engineered piece of DNA back where it would work, into a mouse mammary gland. The only way to do that is to start where a mouse itself starts, with a fertilized egg. This is the trickiest and most uncertain stage of genetic engineering. Fertilized mouse eggs, each smaller than a pinprick, are manipulated under the microscope with delicate surgical tools. A suction tube grabs an egg and holds it firmly. Then a needle, much finer than a hair, pierces the egg's outer membrane, enters the cell nucleus, and through it are injected many copies of the engineered gene. The fate of all these engineered genes is completely unpredictable. The hope is that at least one or two of them will find a safe home among the genes of the mouse egg. Alan Smith and his team injected hundreds of mouse eggs. Then each egg had to be checked to see if it had taken up the new gene. And there was only one way that could be done.
The egg was then reimplanted into a surrogate mother, and then the animals were born. And of course, then we had to ask whether any of the animals that were born contained that DNA inserted into its own DNA.
Some of the baby mice, just a precious few, did contain human DNA among their own. Now the question was, would they actually produce human protein in their milk?
What'd you do today at work, Daddy? I milked mice. She
They did.
doesn't look happy.
The amounts of material that we made in truth weren't very great, but those first animals clearly established the principle.
Oh my gosh.
For the
Quit
first
doing this to
time,
me.
a non-human animal was making a human protein. But as the raw material for a new industry, mouse milk has obvious disadvantages. What was needed was a bigger animal, an animal that makes milk for a living. Alan Smith turned to Tufts University Veterinary School, which saw the technology as a possible shot in the arm for an ailing rural economy. Frank Lowe.
My interest as dean of the school was to help New England find a new agriculture, a smart agriculture, to replace the traditional agriculture of this region, dairy farming. Dairy farming is in decline, sadly. So we wanted to find another dairy animal whose milk would be valuable for reasons that are different from the traditional reasons.
Goats were Tufts animals of choice. They make a lot of milk, and their gestation period of 5 months is about half that of a cow's. An important fact for a technology you don't know has worked until animals are born. The human gene they hope to transplant into goats is for a drug used to treat heart attacks.
One that dissolves blood clots.
A couple days after they're born, they will be
15
tested
minutes after
for
heart attack, they won't have any
the transgene, whether they contain the transgene or not. And once we identify a transgenic animal, then we have to let that animal grow to maturity.
The human gene that's been injected into a fertilized goat egg makes a protein which dissolves the blood clots that can trigger heart attacks. As a drug, such a clotbuster presently costs thousands of dollars a dose. The hope is that the baby goat about to be born will produce millions of dollars of the clotbuster in its lifetime.
They actually call it fooling goats. I have to help her.
Good girl. All black, huh?
This could be the most valuable animal ever born.
Get the phlegm out of his lungs.
Oh, no.
Now, the second goat is enraged.
That's what
But this time, there could be a disaster. The kid's head is bent backwards. Pulling it out could break its neck. It's a common enough problem to confront a veterinarian, and nothing to do with the fact that the kid may or may not contain a human gene. But the chance that this single goat, if born alive, could produce enough of the clot-busting drug to treat hundreds of heart attack victims raises the stakes enormously.
Yeah, why is he yelling
Oh,
at
my Lord.
The kid is 5.
Listen, they talk about the
Mothers
biology.
and biologists are exhausted.
He didn't do
We can
anything.
say the certainties of science meet the
Now listen why they
uncertainties
call
of nature.
baby goats kids. Listen to them.
You are.
What is he opening this one for?
Listen now.
Those are the first
They pick him up. Sounds just
The
like a
kids
human
are taken
baby.
away from their
Well, that's why they
mothers
were,
and
that's
fed
why baby goats are called kids.
Usually the mothers clean and nurse their newborns, but these kids are potentially too valuable to risk the passage from mother to kid of disease.
Aren't they cute?
2 days
Not
later,
like sheep,
these
they're
kids
smart.
were tested to see if they contained human DNA. They didn't. They are, after all, just ordinary goats.
Failed.
Rome wasn't built in a day. We knew that in our minds. We didn't know it in our hearts. It's work that requires infinite patience, great attention to detail, and Murphy's Law is played out repeatedly.
As the Tufts team continued to struggle with Murphy's Law, elsewhere, the technology was already paying off. Edinburgh, Scotland, the location of a company founded on a mouse. The mouse was the creation of John Clark. Clark took the basic idea behind putting a valuable gene into a mouse, but changed the details. One day in June 1990, after hundreds of mice had been manipulated, he ran a standard lab test on the latest. Its human gene wasn't just working, it was pumping out unprecedented quantities of human protein.
So, I mean, what else do you want to do in that situation when you've made such a breakthrough? We went straight down to the pub. I showed it to my two colleagues who were in there. It was still flushing around in the staining bucket at that stage. So I think the people in the pub must have thought we were really crazy as we ordered yet another round to celebrate the achievement. Not so much our achievement, we felt, but the achievement of that particular mouse. It was a great mouse.
But in this part of the world, sheep are the animals that count. A company was founded to move John Clark's mouse breakthrough into sheep and commercialize the production of human proteins in their milk. One of these proteins is factor IX, used to treat people with hemophilia. Another, called AAT, could be used to treat a deadly genetic lung disease. Already, some of the sheep are producing 30 grams per liter of human protein in their milk.
Some of these are factor IX, and one of them at least is AAT. The mammary gland is a mammalian system by definition, and it turns out that it's a very good factory. Our sheep are little furry factories walking around in fields, and they do a superb job. This is a litre of milk from one of our transgenic sheep. And if it was the sheep that contained 30 grams per litre, that is the amount of protein that would be contained in this litre of milk. So first of all, they do the chemistry, and the second thing they do is they make a lot of it, and they do it very cheaply.
30 grams of the company's first product, the drug to treat lung disease, is worth over $1,000. The sheep that make the drug are worth hundreds of thousands of dollars. For security reasons, only the company knows which animals are drug factories in sheep's clothing and which are just sheep. The fear isn't only of theft.
Animal rights people
Police say they're
the
not
lab
yet
to
linking
kill
the
animals
incidents
to
with a
protest
fire that was
using
deliberately
animals.
started at another animal research centre at Pennycook, and the fire
In Britain, the animal rights movement has taken a militant turn in recent years. This firebombing was of an animal research laboratory near the Sheep Project.
Jane Frankie, BBC reporting Scotland, Banbury.
It dramatized the opposition many people have to what appears to be yet another way humans have found to exploit animals.
Of course, we are concerned about those people who hold very deep-seated views on the use of animals, the so-called animal rights people. And for many of them, it's just a firm belief that you shouldn't use animals at all for anything. You shouldn't eat them, you shouldn't take wool from them, you shouldn't take eggs or milk from them. And for those people, there really is no way that you can present a logical argument. Then there are other people who quite legitimately are worried about cruelty or harm to animals. And with those, we don't really have a problem. because the process that we're using doesn't do the animals any harm at all. They still remain sheep, they behave like sheep, they've only got one tiny single human gene in, so they're not harmed in any way. And the view of the man in the street really is that if we're doing this kind of thing for healthcare reasons, to cure other people, and it's not doing animals any harm, then they're not particularly concerned about it.
So when I look around this room, I look at this room of experts who are narrowly
In the United States, Jeremy Rifkin is a Washington-based activist who has argued from the earliest days of genetic engineering that it is dangerous and exploitive.
The motivations behind this research may be honorable, but the inherent nature of the technology is engineering. What are engineering principles? Quality control, predictability of outcome, efficiency, quantifiable standards of analysis. These are engineering principles. Do we want to embark on a journey where we apply those engineering principles directly to our offspring, to other living creatures, to future generations? That's why we call this genetic engineering. Now, of course, living creatures are different than inanimate machines. Yet we have tools now that allow us to treat living creatures like inanimate machines. And that's the question before the human race in the next 5 decades. Do we embark on a journey that could last 500 years in history where we reduce life itself to engineering standards?
These are the kind of fundamental questions, the ethical, the moral questions, that the biotechnology industry and policymakers need to address, rather than the short-sighted views of profit and the illusion of progress. I think part of the problem is that a lot of people have become enchanted with biotechnology, a kind of technological enchantment. And there's an upper layer of technocrats who feel that this is the wave of the new world order, that it will fail if the attitudes towards the rest of creation fundamentally remain unchanged.
The arguments raised by people like Jeremy Rifkin and Michael Fox address fundamental questions about our right to tinker with the genes of animals, as well as the wisdom of doing so.
Putting human genes into sheep or goats is unsettling to many people because it seems to violate the rules of nature. In nature, different species can't interbreed, and so they can't exchange genes. But in fact, we've been moving genes around within species for thousands of years, ever since we started farming. Our domesticated animals, like sheep and goats and cows, have been bred by deliberately selecting for the genes that give more wool or milk or meat. And one animal above all others shows how spectacularly we've been able to manipulate genes long before the age of biotechnology.
Think about all the different breeds.
Down the ages,
We did all that.
dog shows have been a celebration of just how much we've been able to reshape nature. A few thousand dog generations ago, all dogs were wolves. By breeding together dogs with desired qualities like size, shape, or temperament, breeders have produced hundreds of different varieties. But there's always been a limit. All dogs are still only dogs. We've never been able to introduce into a dog even the slightest trace, for instance, of a cat. But today, even more improbable crossbreeds are a reality.
Here's one of yours.
This is Herman, who grew from a fertilized egg into which had been injected a human gene. Every one of his cells has tucked away among its 100,000 cattle genes that single gene for a human protein. Herman lives a pampered life in a barn in Holland, where he's the property of a U.S.-Dutch joint venture.
What do you think, Hans?
He's very honorable. He looks excellent. We've certainly invested a lot of money in doing this. There's been $10 million that's been invested so far in developing transgenic cattle technology, and Herman is a result of that. And he also represents the beginning of a new era in the dairy industry.
Herman, of course, produces no milk. But in May 1992, Monique was born. And the hope is that she too may possess the same human gene Herman does. Soon, Herman could be the founding father of a new breed of dairy cattle that would all now produce milk containing the human protein. It's a first step toward redesigning cow's milk to order.
We're not increasing the quantity of milk being produced, but we are changing the quality, making milk which is going to be lower in cholesterol or have different nutritional characteristics, so that it's more suitable for human consumption. The glass of milk needs to be fiddled with. We see a situation where, 50 or 100 years from now, there are many different types of cattle available making different types of very specialized milk.
One of those specialized milks could be made with human genes, to be more like human milk.
Are you hungry? Huh? Can you have me, sweetie?
Do not do that on camera.
Human milk differs from cow's milk in many ways. One of the most important is that mother's milk contains a substance called lactoferrin that helps babies cope with infections. An infant formula made by cows containing the human lactoferrin gene could produce a big payoff in the billion-dollar formula market. And in fact, the human gene Herman possesses is the gene for lactoferrin. Soon, his offspring will be making it by the gallon. And if we can give cows the human lactoferrin gene, why stop there? In principle, cows could be re-engineered to make milk that's as human as our own. And if animals can manufacture human milk, what else can they make? In the U.S. alone, donors need to supply some 70 million units of human blood a year. In the age of AIDS, all that blood has to be screened for the HIV virus, as well as being typed, sterilized, and stored. It's a cumbersome, expensive process. In principle, there's an alternative. The key component of blood needed for transfusions is the red blood cell. These cells transport oxygen around the body through our arteries and capillaries. And the key component of our red blood cells is hemoglobin, the red-colored molecule that actually picks up the oxygen. Pure human hemoglobin could have advantages over whole blood in many medical emergencies. The question is, where to get it from? Deep in the Ohio countryside is a prototype factory for making human hemoglobin. Paul Schmidt is CEO of DNX, the company that owns the plant. But even he has to take special precautions before entering. No disease can be allowed to threaten the human hemoglobin made and stored inside, in the arteries and veins of pigs.
This is Wilhelmina. This is a real special pig. It's the very first transgenic pig that DNX developed. About 10%, maybe better over hemoglobin is pure human.
Wilhelmina is the product of a simple idea, that there could be an immense and lucrative market for human hemoglobin.
So what we had to do was come up with a way, a biotech or recombinant way to produce human hemoglobin cost effectively so that you can take advantages of a source of supply that's free of AIDS and hepatitis that can be produced in unlimited quantities. Doesn't require cross-matching, can be stored on a shelf maybe up as long as 2 years, so it doesn't have to be kept in a frozen environment. And what she has proven is that we can probably produce it for a reasonable price and make this exciting capability available to the whole world. Workers pigs know how valuable they are.
They certainly won't be bacon, will they?
Pigs are a very valuable animal when it comes to healthcare. Diabetics have been treated with porcine or pig insulin for well over 60 years. Pigs today provide left ventricular heart valves for transplant into humans. So pigs have always been a very valuable animal.
But until now, we've always made do with the pig version of what we lacked. DNX set out to make pigs that would make our version.
First of all, our scientists assumed, and they turned out to be correct, that if we genetically engineered a pig with human hemoglobin, because porcine or pig hemoglobin is so similar in structure and function to human hemoglobin, that you'd have a healthy animal that would reproduce efficiently. And that's critically important because if you consider the fact that starting with one founder transgenic boar, because pigs are a litter-bearing species, they reach maturity in a relatively short time frame of 6 months, the breed up is incredibly rapid. Starting from that one boar, within 3 years we can be producing $300 million worth of product. In 4 years we can be producing $1 billion worth of product.
One step away this
Between
year.
DNX and the commercial bonanza stand many hurdles.
We're worried about pig diseases.
Will pure hemoglobin work as a blood substitute? How can the safety of human hemoglobin made in pigs be absolutely assured? But these aren't the only questions facing the companies aiming to give pigs and other animals human genes in order to provide a new source of supply for the biotechnology industry.
The products of the biotechnology industry are undeniably valuable, both in human and financial terms. But this masks a central philosophical question. We already raise, fatten, and slaughter pigs for their bacon. Is there a difference if we raise, fatten, and slaughter them for their blood, or rather for our blood the pigs unwittingly produce? Is the promise of this cheap, AIDS-free human blood substitute from pigs another triumph for technology and private enterprise? Or is it an example of how, as we gain power over life, we debase it? We're using living creatures as factories. Factories have to make a profit on their investment, and the investment in the biotechnology industry has been immense. This means someday soon, it has to start selling its products to a mass market. Many of the early products will only ever have a tiny market. Factor IX for blood clotting is a good example, enormously valuable to those who need it, but not likely to generate huge revenues. So where is the profit to come from? Will it come from products being developed to sell to people who never knew they needed them? Human growth hormone, for example, was developed by the biotechnology industry to treat dwarfism. Already, it's being used to treat people who are simply short. What will happen as more and more products pour out of the biotechnology pipeline?
The first product of biotechnology to seek a mass market also happened to be a growth hormone, not aimed at people, but cows, and not to make cows grow, but to give more milk. Almost at once, the biotechnology industry found itself enmeshed in the complex politics of the dairy industry. This is the farm of Bill and Jenny Nelson in northeast Vermont. They are typical small dairy farmers, able to stay in business only through hard work and the existence of a price support system designed to allow them to compete against larger, more efficient milk producers. So when the Nelsons first began hearing about a bioengineered hormone called BSD that boosts a cow's milk output by more than 10%, they were appalled.
We're already dealing with a huge surplus problem anyway in the country, and this is just going to irritate that situation even worse.
That all by itself lowers the price for milk. So it's in our best interest not to have a surplus. BST would almost guarantee that there would be a surplus of milk.
Cheaper milk threatens the Nelsons' already precarious place in a dairy industry that has been driving toward greater efficiency for a century. So BST began running into opposition from some of the very people its manufacturers had assumed would welcome it.
People could do it, and so they did do it. They could make a protein that mimicked a growth hormone, and so they did. And I don't really think they asked the question about whether we needed more milk first. They were probably more interested in the profit opportunities in a product that you can give to really hundreds of thousands of cows every single day.
It has no redeeming social value. It's bad for the farmers, it's bad for the cows, it's bad for the rural economy.
As part of his long-running battle with the biotechnology industry, Jeremy Rifkin quickly seized on BST as an example of what is wrong with biotechnology. He began a campaign that led to one dairy state's banning BST.
That this product makes no sense and certainly has no place in the economy and the markets in the state of Wisconsin.
Economic suicide.
Another argument used by BST's opponents is that by increasing milk production, the hormone will also increase the risk of udder infection. So farmers may have to use more antibiotics than they already do today. While concerns like this have so far held up BST's approval, the most emotional issue in the BST debate remains the deceptively simple question: is it good or bad for farmers?
My view is that yes, it will drive some small farmers off the land, but it will make other small farmers more profitable and more secure. The evidence is that the management acumen of the farmer is all important in the successful use of this stuff, so that the better managers will do well with it and others won't. Nobody will ever force farmers to use BST. The farmer, after all, has to pay for it. Presumably, a farmer won't buy it unless the product does what it's supposed to do. I would argue that the technology might make sense in some regions of the country and make less sense in other regions of the country. If farmers in Vermont find this technology not in their interest, but the farmers in California do,
Exactly what happened.
how do we make that kind of national social decision?
The decision rests on whether more and cheaper milk is of greater value than keeping small farmers like the Nelsons in business. Whether BST is a good thing or a bad thing depends on how it affects what you value most.
This 946.
Farmers today are business people and are under enormous economic pressure, yet they believe there are values issues associated with things like biotechnology, the use of BST. So I'm all in favor of looking at values issues, but it will open a Pandora's box because we have never done so in this country. You could argue that introduction of the refrigerator was wrong because it put icemen out of business. Where does one stop doing that? Very tough question. That's why I think the more these issues are discussed, the more widespread will be the appreciation that technology and values are really intertwined.
The debate about biotechnology has broadened dramatically as its products begin leaving the lab for our tables.
At 7 a.m. on June 2nd, 1987, preparations were well underway at Monsanto Company for a historic event. This day marked the first time that a food plant, engineered to contain new protective genes, would be taken out of the greenhouse, planted in the open field, and allowed to flower and bear fruit.
The tomato is the first of what could become a steady stream of food crops containing foreign genes that make them easier to grow, transport, or store. For the companies making these genetically engineered crops, the public's reaction is critical.
That the technology works and can help farmers produce crops more efficiently. The Jerseyville community was supportive of the test, and the media coverage was positive.
Right here in this farm field, the genetic engineering revolution in food crops began. Al Wyman, News for Your Health, in Jerseyville, Illinois.
In 1993, the first genetically engineered tomato went on sale. Normally, tomatoes are picked green, so they won't rot before they reach the supermarket. The new tomato has an added gene designed to cancel out the gene that triggers rotting, so the tomato can be ripened on the vine. The U.S. Food and Drug Administration has decided that the new tomatoes and other genetically engineered crops that may follow them to the supermarket need not be labeled. This ruling has alarmed some environmentalists and consumer advocates.
Well, one of the issues is whether or not we're going to be able to trust our food when we know that genetic engineers are adding genes to it. I think we're not going to be able to trust the tomatoes of the future the way we've trusted the tomatoes of the past. In the past, we know inherently what's in a tomato, what makes a tomato. That trust is about to be shattered by a technology that can now put a human gene, a pig gene, a carrot gene, a bacterial gene into this tomato. We're not going to be able to trust the tomato of the future in the same way. We're not going to know what genetic engineers have done to it. In that way, it's going to be a lot more like processed food than like whole food has been in the past.
I'm going to skip through this one to the
This
last one.
unease about genetically engineered crops sparked a protest that
This is a bunch of rich chefs at $200 a plate restaurants that say they'll never buy genetically alternated food. You know, who can afford $200 a plate? The last point I want you to get is the biggest thing that looks very, very possible and probable, and that is where you're talking about
a vigorous public debate should precede their arrival in our stores and on our plates. But even as that debate takes place, the powers of the genetic engineers are rapidly expanding.
Despite its awesome promise and investments totaling tens of billions of dollars, biotechnology's practical fruits are still rather modest. A few foods, a few drugs.
You ever had
The
broccoli flour?
main technical problem is that inserting a foreign gene into a plant or animal cell is still a very hit-and-miss affair. It's not much more than taking a lot of copies of the gene and scattering them into the genes of the host in the hope that by chance one lodges in a place where it can make itself at home. What genetic engineers would like is the ability to slip the gene into a predetermined spot. Then they could put genes anywhere they wanted and truly begin to design life to order.
This power to manipulate genes much more precisely has already been achieved with the animal it all began with, the mouse.
Move any gene we
Today,
want in there,
it is possible to place foreign genes into the mouse exactly where the genetic engineer wishes. What's more, genes the mouse already has can be precisely knocked out.
UCLA has a mouse.
A new industry has already been founded on this new precision genetic engineering. Mice can now be created, for instance, with human diseases. This will enormously simplify the design and testing of new drugs. And as before, where the mouse leads, other creatures will follow. We may be on the brink of a profound revolution in the treatment of chronic disease.
I think in 10 years, you'll have this. You can grow your own heart. You need a heart transplant.
Many life-threatening diseases affecting the body's major organs, the heart, liver, lungs, kidneys, can be cured by an organ transplant. There are currently two major barriers to organ transplantation: a shortage of donors and the problem of organ rejection. both problems in principle could be solved by the new breakthrough in genetic engineering. This is a miniature swine. Its major organs are about the same size as a human's. Swine can't be used as organ donors today because their genes label their organs as a pig's. Our bodies would reject them. But what if these pig genes were replaced by genes that identified their organs as human, even a specific human, say you or me? Then, if we needed a new heart or kidney, a pig could be genetically designed and created to produce a tailor-made one, just for us.
6 months.
This scenario is still science fiction, but only just.
We're now on the brink of being able to design living creatures to order. We're already doing it with the most humble of our close relatives, inserting and knocking out genes at will. How many human genes could we put in before it becomes something else, a mouse no longer? And what we can do today with a mouse, and tomorrow with a pig, we'll soon be able to do to even our closest relatives. There's only 1 or 2% difference between our DNA and the DNA of a chimpanzee. And of that difference, probably only a few critical genes really count. Where will we draw the line? Which human genes should we not transplant? What about genes that affect intelligence? Should we ever find any?
You're worried about making...
As we blur nature's boundaries, technological and financial imperatives are hard to resist. Can we keep a grip on our ambition before we pass the point of no return?
Sorry, I tossed it in there.
Chimeras, creatures part animal, part human, are no longer simply fantasy. And what we make from the life that shares our planet is now limited only by our imagination, and one would hope, our good sense.
Did you flip on the lights for me? Okay, so that's everything for the test. You done it. You may now go home. I'm going to go over that. A lot of people thought, well, what are the different kinds of plasmids? You only have to know the F plasmid. But these are some of the plasmids they have discovered.
So, but we don't need to know none of this, right?
Just the F plasmid.
Just the F plasmid.
You just need to know that not all plasmids are F plasmids. All right. What else? Conjugation, the significance of conjugation. It's huge because if we had to discover conjugation, we wouldn't discover plasmids. If we didn't discover plasmids, there would have been no recombinant. Remember, when we took that human gene and knocked out the introns, we put it on a plasmid. Then we cloned the plasmid and had it jump into the E. coli because plasmids rule. So without conjugation, we would have never done recombinant DNA technology. We wouldn't have human insulin or human growth hormone. Okay, and so remember the conclusion. It has had a large effect on evolution of the gram-negatives because it can move up to 51. But nothing else. Okay, so that leads us to our little video. And maybe it'll work and maybe it won't. We'll see. Did you hit the VCR button? We'll see if this thing will play or not. I am unsure. If it doesn't, I'll just talk about it for a few minutes. Everybody got a copy of the sheet, worksheet? Anybody need one? One of them you can already answer. Why don't we call it genetic engineering anymore? Yeah, that's it. Oh, okay. Okay. All right, so,
I forgot the question. Does the P line make it, the S, or does the
No.
F gene make it?
the F gene makes this pilus.
Okay, so
Codes
can
for
you
the
have the
pilus.
F gene without having that little P line or whatever?
No,
Okay, so the F gene, you're
but you
always
can
gonna
have a
it.
plasmid that doesn't have an F gene.
Okay.
There are 36 different kinds of plasmids, only
Okay.
one of them is an F plasmid.
Oh, yeah, okay.
And then once it transfers it, the other one grows little pili too, right?
Right, because the first gene that's transferred is the F gene. So first it finds a girlfriend that doesn't have an F plasmid, and then it doubles itself. Then it makes a little tube, and the first gene that's passed is the F gene. And if allowed too long enough, it can transfer the whole plasmid.
Can a donor cell have more than one F?
Yes. Okay, so, and you know, they can also conjugate with more than one at once. All right. We've also found that plasmids, if you bring this, remember most of the time, is between 2 gram-negatives that are closely related in the same genus. But remember, there's Streptococcus, it's a ho-ho. Actually, it's a slut. She doesn't get paid for it. It will have sex with anything. It doesn't matter if it's eukaryotic, prokaryotic, it's in the same genus or not. And then we have the races, Homophilus and Neisseria, that will only have sex with the same genus and the same species as they already are. So that's not getting recombination. They're already having sex with somebody that looks just like them. So anyway, this one does move a lot of DNA, but in nature, it's very restrictive because it's usually between the same genus except for Streptococcus. Okay, so it can, however, move 51. I'm not going to go over that.
But for a life-saving drug they produce in their milk,
I don't think that. I don't think that.
to some, they are an exciting portent of the future.
So what I see when I see a flock of sheep, well, I see profits, of course, in the future. Some return for the investors of the work that we've done so far. I also see a living embodiment of a piece of very clever science, something that started off as an idea. It's now there and it's working.
To others, the science that has created these sheep to make drugs instead of wool is taking the exploitation of animals too far.
This
They got two weird
raises
people. They got
profound,
somebody that's against everything
medical,
and somebody that's for
ethical
everything.
questions. It's altering
He's against
the
everything.
created order, and I think there's something profoundly subtle that we don't fully understand about the created order, and we shouldn't mess with Mother Nature to that degree.
The sheep on this research farm look and act just like any other sheep, but they are worth tens of thousands of dollars each. What makes them so different, so valuable to their owners, so disturbing to some critics, is that tucked away within the 100,000 genes that make each of them a sheep is one gene that comes from a human.
Throughout history, we've been fascinated and haunted by the idea of creatures that are part human, or humans that are part creature. Chimeras, they're called, fantastical imaginings.
From the centaur, part horse, part man, of Greek mythology, to the monster myths of the 20th century, the idea of merging animals with humans is profoundly unsettling.
You already know number 17, I already told you about it.
Enhancing life. Up John.
new life begins. An embryo grows and divides. What it will become, mouse or elephant, pig or person, has already been decided by the genes it inherited. Only mice pass on mouse genes. Only people pass on human genes. Until today. Because today, science has broken the barrier that separates species. Today, elephant genes can be put into mice, fish genes into tomatoes, human genes into pigs. We have begun to design life to order. Some of these designer animals are already grazing the hills of Scotland. They are owned not by a farmer, but by a new kind of company, a biotechnology company. And they are being raised not for their wool and meat.
You can already answer number 4. You can also answer number 2 already. What was the first organism to put human genes in?
A sheep.
The first organism on Earth that received the human gene. E. coli, human insulin. Number 4, I already told you what transgenic is. Yep, eukaryotic to eukaryotic. See your mind.
Dr. Gates?
Yeah.
For midterm, you wrote second LP midterm exam. Are we actually having a lab practical or just?
Well, because it's on the cards, it's called a lab practical.
Oh,
I have a feeling I may have to go through. What?
Is eukaryotic prokaryotic?
I'll try this one.
DNA transfer, right?
Unlikely that it will work. Oh, this one should work.
should we have no?
So read through the questions real quickly so you're familiar with them. You can answer 11,
Oh, quick question on the
9.
Lucille P. Markey Charitable Trust, the George
I'll
P.
give it
Smith
to you.
Fund, the Corporation for Public Broadcasting, viewers like you, and the people of the Upjohn Company.